Gosh. Hey, just FYI, I just clicked started live.
Yeah. Oh, we're started.
Oh, okay.
Okay. All right. Cool.
Well, it just takes me a while, so
Okay.
I
I'll share the notebook. I have the notebook here.
yeah, I'll put
Yeah.
on
Just you do the last part.
I'll,
Uh,
I'll put on the what is that? Is that a different one? Um, I'll
all right.
share. What should I share? I'll share. Okay, so you're sharing. Okay, perfect.
So, okay, are you sharing the companion or
I
something?
was just about to do that. Yeah, I have
Okay.
it. Let me stop screen share and
So we're on
reshare.
convolutions. Um, yeah, we did some good work. I know Michael and I went through convolutions, and I know you went through it later, John. And I spoke to you a bit about it. I kind of forget. I remember we got through everything with a good understanding. I kind of forget some of it,
Uh huh. I forget it
as
too.
usual.
Yeah.
Here, I guess we'll start it.
So I have the companion. I should be sharing that on my screen, I think. Yeah, and then you
So,
have the book. Oh, you have the website.
yeah, I have the
Okay.
book.
All
And
right.
I have Wiki because I've used this a couple times and it re-jogs my memory
Oh, yeah, I
because
went through a couple
Wikipedia
of
does a good job.
supplemental videos on this as well.
Yes. Yeah, I went through a video or two as well.
Khan was okay, but we found that other guy who was
Yeah, yeah. So Khan was well. Let's get into that in a second, actually. So very at the very base level, like convolution. Sorry, someone's calling me. Gotta hang up on them. A convolution is just a function that produces a third function, and that third function is the shape of one of the functions modified by the other.
yeah, it says that what you have right there, it says convoluting refers to both the result and the process of actually doing it.
Yeah,
So it's
I remember
defined as
talking
the
about that.
integral of the product of those functions after one is reversed and shifted.
Yes.
What do they mean after one is
Um,
reversed and shifted? Oh, that's where the g t
Using a
minus
t
tau.
so
minus
that's
bar.
what the t and t
Yeah.
minus tau is
Got
right
it.
there. And it so okay, so it's shifted by t. So t is kind of just like a constant in
But
this
where
case, if
would
I
you
remember
ever
correctly.
get the intuition to do this?
And
Right, and I see the
Again,
overlap.
recognition.
y- yeah,
This is what I mean. My original example is the only practical application I can think of is moving a box. So if you can do rotation like we do in this chapter, and you can do uh, the convolution, which moves it around, then you essentially can do everything necessary to train a CMN.
Yeah, I mean that in your
I guess
example, it makes sense to me, right?
Yeah.
Right, and I get that.
you're like, how do you come up with the
Yeah,
convolution
yeah, yeah, yeah.
formula
Like,
like this? Yeah, I mean, I think you would
well,
probably,
because
have this in your head,
this is the generalized
right?
formula. It's
So
not.
my whole theory is that people like as we become more advanced, we abstract think about things. And so what happens as a result is we forget how we arrived at the original conclusion. And if we continue this way, eventually people are going to forget how basic things work.
Okay, but okay, so
Like this, and so we've forgotten how this
yeah,
works
but if you
because
read the
we've been around
historical
for
development
So,
section that Shane's looking at, it came. The
um,
guy made it in 1754.
yeah.
so I mean, I would imagine, John, that you kind of have, you have this in your head, um, and you're trying to come up with some like moving, like weighted average formula and have one function shape the other, and then once you have like the visual, then you kind of backwards engineer to the general formula. That's
Yeah,
an
I
easy
guess
guess,
the
but that makes
reverse
more sense to me.
the reversing part is, or the translation
Oh,
part or whatever. I don't really understand that, but I guess can you scroll up for a
what?
second? And there's each one of these boxes. Can we just Can we just go over
Yeah.
that, the visual explanation? So what does it say?
Yes. Express each functions in a dummy variable, tau.
Yeah.
Okay. Reflect one of the functions,
Okay,
t
wait. So let
tau.
me see that they did that. Okay, so the red
Or maybe
one.
right, they literally just reflect it's backwards.
Okay, so the
Yeah.
red one got reflected across the y-axis. Okay.
Yeah.
Mm-hmm. And then move
Add an
it.
offset.
Yeah.
Yeah, so that's the offset t. So you need to, so because you're like, because it's going from left to right, I guess you have to offset it to be on the left of the original function.
Yeah.
Right. I think I can
You
kind of.
probably could make it go from right to left if you want and change the formula, and I think you kind of get the same thing.
Yeah.
I guess maybe we think left to right or something.
Well,
Okay,
you,
so
you pick
start
you
at
pick you pick one function to be convoluted by the other. I think that's really what it is. So if you did it the other way, you're switching the functions.
oh, I was saying like if you did it the other way and then like you still made
Yeah, but what would
the
your
second
integral
function
would
go.
be backwards then, right?
Yeah, yeah, that's what I was saying. You'd have to change the actual
Yeah, no, it makes more sense this way actually. I think because and they also
well, you're going from negative
That's
infinity
what I'm
to
saying.
infinity.
That's what I'm saying. Yeah, yeah,
Right?
yeah. And you're
Yeah,
picking one function to be convoluted by the other. So I think
yeah.
kind of actually that part makes sense.
So
Um,
reflect. Yeah, that actually does. So you okay? So you reflect it. You bring it to the left side of the function with a time offset. Start t at negative
right.
infinity, and you go to infinity. Obviously, you want to do
And
the
you
whole thing.
start moving it toward the other one.
Computing a sliding weighted sum of the function.
Right. So you're like
Um,
almost Riemann summing. You're taking it and adding up the overlaps, right? As you move over it.
yes, yes.
Okay, and then you're saying like so right away that yellow thing right there. Uh oh, is that a weighted sum? Because it looked like wait. So maybe we should
The
just
integral is the slided weighting sum.
what's weighting? Like why is it weighted? Like I feel it
Um,
looks cumulative to me. Like when it slides over at least in the next visual. I mean, maybe I'm jumping ahead here. That might be the
well, I know the textbook makes it very clear why it's weighted, because they give an example of blurring images, and it's very easy to see how they what the weights are. I think they call it the
so the
point spread
weighting
function,
function is the
but I don't
reflection.
know about here.
It says if you keep reading, it says the weighting function is
Where's
the thing that you highlighted. Just keep reading.
oh, where the weighted function is the reflection.
Hmm. So that's the
Yeah.
weighting. That's what's weighting it. Oh, okay.
So
Okay. Oh, that's all they mean. That's all they mean. Okay, so it is cumulative, but it's being weighted by that function, right? That function's what's
Yeah.
giving weight to each piece of the original function.
yeah. And that's called I believe the point spread function. That first weighted function. So I don't know if you guys remember from the book, but we're getting the convolution of these two matrices, and I'll show you the image below so it
Oh,
makes a
okay.
little bit
Yeah,
more
so this
sense.
each
So
pixel's
you
an
have going,
average of the blocks that are around it.
yes, exactly. So
Yeah.
that's yeah, exactly. So B, this is called the point spread function. Um,
Okay, no. So that's called the point spread function, but a convolution could be anything. It doesn't have to be point spread.
yeah,
This one's point
yes,
spread because it's like saying, at any point.
yeah. You're getting the average of the 4 points or
Yeah,
whatever.
yeah, yeah, yeah. So
In this
okay, so
case,
this
the
is the
convolution is
right. So this matrix
yeah,
represents some function that's going to give you adjacent
on
points.
X.
Yeah, yeah, yeah.
Yeah, which you end up getting this. But I
Okay,
was just saying,
okay,
it
okay.
makes it clear to see the weights because we could set these weights to they don't have to be a quarter. Like you said, they could kind of be
They could
anything.
be an eighth. They
So
could
that
be.
so if you made them different,
Right.
it would be a different weighting. Like maybe the bottom right pixel holds more weight
For
for some
whatever
reason than your
reason. Yeah,
average.
yeah. Right.
Um, okay. This isn't is it for how complicated, it took us to get to this point. This actually isn't too bad.
Can you go back to that
Um,
wiki page real quick? Can we just finish up
yes.
the three sections? Sorry, I just don't mean to waste time.
I'm
I don't
opening it
ever
up.
feel good if I don't. Geez, you got a lot of tabs there, man. What's that database you have next to Chrome? Is that's
Next to Chrome. Oh,
yeah.
that's I had to use it in school when I was had a SQL course. It's like a SQLite database or something.
Oh, SQLite.
Oh, okay.
That's
Yeah.
hilarious. Do you
No,
know
no, 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 no. Yeah. Wait, what were you gonna say?
SQLite is a fake database? So SQLite
Yeah.
is a
No,
database that
it's not real.
ships with IoT devices, and it's like it's just a bunch of files, and you might have an interface there that reads those files like it's a database, but it's fake.
Yeah, it was for learning purposes, right?
Okay.
Which makes sense why they would do that. Okay. So then the last,
Wait,
so
what's the
the
middle one?
resulting wave,
Oh yeah, right, right. Sorry. Go
the
ahead.
resulting waveform not shown here is the convolution of functions f and g.
Yeah, I mean, and they
Um,
show it in the visual, like the
yeah, this
line that gets
line,
drawn. Yeah, yeah, yeah. Whereas in the
that's the
second
result. Yeah.
one, so I guess it could be. I don't know. That's interesting that they're calling it a wave. I guess it is a wave depending on the other function. They're
Yeah.
just trying to make a simple functions, but
Yeah. Well, that actually does make it see how much overlap. When they're completely overlapped, you're at one, and
right,
then
right, and the function itself is what's doing the weighting. It's a cumulative, wave. I think it's a cumulative wave resulting
yeah.
waveform, but the function itself is causing the weighting. Because the function determines how much overlap there is.
Yes. Yeah.
So what's the
If
second one? Oh, keep going. Sorry.
ft
Yeah.
is a unit impulse, the result of this process is simply g of t. A unit. What's a unit impulse?
It means move on. Dirac delta function.
What the hell?
Density of an
Equals
ideal. Oh,
zero
it's total
everywhere.
physics. Yeah, it's
Whose integral over the entire thing is one.
ideal.
Uh,
Wait, mouse over it. Yeah, because it's an okay. So it says it's an idealized point mass or point charge as a
So
function.
it's a uniform. It's a uniform distribution.
Yeah. Okay. I don't know. It's super weird. Um.
yeah, I see.
Oh well, yeah, he's right. If it's uniform, it's just going to come out to g of t,
Yeah,
right?
if
It's
it
just going to
equals
come out to
one,
be
but it
whatever.
also equals one, which means the
It doesn't.
probability
It doesn't matter that it's offset, right? Like think about it this way. Like it's a It's a. I'm sure it's more complicated than being a uniform, but let's just say it's uniform. For example, you slide that left g of t function over the thing, and you're just going to get g of t back at you.
yeah.
You know what I mean, Shane? So like it's sort of making the original function irrelevant.
I see what you're saying. You slide your first
I think
function,
it's
the
like it's
original
like the
function.
ID function in lambda calculus where you just literally get back what you gave it. It's like
Yeah, like
kind
the
or
identity
the identity
something.
matrix. Yeah, 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 something like that. A
Okay, I
unit
see.
impulse, right? So for every
Okay,
unit that's happening, it's got sort of giving you back whatever you gave. It's not convolved. It's not changed by
okay,
you know. All right, keep going.
okay. And it says, and you end up getting one. So is this an example of that? Because it looks like you have the same
No,
for the
no,
first
because
one here.
that blue box. No, because the blue box starts at well for at a point, I guess, but
Oh,
doesn't it
at the
need to be
point.
like it
Okay.
everywhere?
Oh,
Right,
everywhere it
because
has
it's
to be.
zero, and then it's all of a sudden goes up to
Oh,
one.
it's zero and then it's one. Some. Oh, I see.
Basically,
I
the
see. I
result
see.
should look like what you
Yeah.
started
So that's
with.
why we have this graph here.
Right,
So
right,
that's why you have this graph here. Okay,
right,
I understand.
right. I don't know. I mean, I have to look at it, but the result should be
Yeah.
what you started with before you even reflected it.
Okay. In this example, the red-colored pulse g of tau is an even function, uh, which is like symmetric, or the reflection is the same, or whatever.
It's
So con
metric, yeah.
so convolution is equivalent in correlation.
So if it's an
Equivalent
e,
to correlation.
yeah. Wait, what'd you say? Say that again.
No, it's an equivalent to
Yeah,
correlation.
they're
How
equal.
is it like
So if you find
correlation?
Equivalent to
correlation,
correlation.
well, the idea is if you found correlation, you could actually set this integral to equal to whatever the correlation is. I gotta sneeze. So if you could prove that they're even, it's an even function. So like Shane said,
Yeah,
symmetric. Like this box is symmetric.
it's probably easier to calculate a correlation.
It probably
Um,
depends, if we're being honest.
maybe. Well, yeah, maybe.
There's probably some derivation that you could create
the
that
point the point is,
prove
But the
it,
correlation.
point is they're the same.
if you but well, here's the point. Here's the point. If you had
And you
one,
could find one.
if you had one, you get the other one for free.
Yeah.
That's a big deal,
Yeah.
because
Exactly.
yeah.
Yep. All right. A
So this one
snapshot of
is this
this
one is an even
movie
function. Yeah, the amount of yellow
shows
of the area is equal
shows
to.
function gt minus tau and f of tau for some value of parameter t, which is arbitrarily defined as the distance from the tau equals 0 axis to the center of the red pulse.
Mm-hmm.
The amount of the yellow is the area of the product, f
Mm-hmm.
tau gt minus tau, computed by the convolution slash correlation integral.
To be honest, I
Um,
don't have intuition exactly on how the yellow is the product of the two of them, but I totally believe it.
yeah. Do you remember? Yeah.
So that
As
means,
far,
so
yeah,
like
I don't really see if.
for example,
Well,
like,
they did it out. Oh, sorry.
well, so for example, when the red goes halfway through, right? So the red goes halfway through the
Yeah.
blue box. It cross the line, the wave that they're drawing. Yeah, exactly. That point right there. It's got to be square root of 2 then, right?
It's well, integrals are essentially the area.
That's what
So
I'm
here's
saying.
what I noticed.
Well, it's
You see that line that it's drawing is that's the area of the overlap.
Right.
when
So
it's halfway over. Wouldn't it be 0.5?
no, is it?
When it's fully over, it becomes
When you're
one.
saying it's
Oh
half.
yeah, you're right. It
So
has to be point
that's not right.
five. Oh, no, you're
That's
right.
just
It's
the
absolutely.
half of it.
Wait, it's the.
Yeah,
Oh
it's the
yes.
area line.
Because
Because
the
the
integral,
integrals
yeah,
are
it's
just areas.
just area. Um, you could see that kind of.
Oh,
I mean,
so
it's kind of hard
so
to.
no. It is. I get it now. So if it's the area, then it is. It is basically just the two functions multiplied, or in other words, the length times the width. Because you have
Yeah,
the
it's the
you have the
area
Yeah.
of
you have the
the
blue function that
overlap.
represents the height, and then you have the red
Yeah.
function that represents the width or whatever, which is the tau
Yeah. The height's one, and
it's the t minus tau. Yeah, that makes sense.
yes. All right, and okay, cool. And where are we? So snapshot of this movie shows function that g t minus tau and f of tau in some value of parameter t, which is arbitrarily
Wait, but
defined as the distance from tau.
can you just explain for me for a second? Okay, so now I know how it gets up to half and it gets to one. Oh, I see. Never mind. Never mind. Go ahead.
And what were you gonna say? Once it gets past the 0
Yeah, but
or
it's
something,
kind
it
of
starts going
obvious because
down.
it starts it well it gets to the full and then it starts losing it
Yeah, and then
again.
it just starts. Yeah. Which Okay, so hold on. Snapshot of the movie g of t minus tau and f of tau for some value of parameter t, which is arbitrarily defined as the distance from tau equals 0. Is the center of the red pulse. Uh, so this is okay. So the
The
center of the
red pulse
red
is
pulse
is
is
yeah. Oh, right,
okay.
right.
The distance from tau.
Wait,
The
wait. Oh
amount
no,
of
go over that.
yellow
Go
is
over
the
that
area.
again. Yeah, say that again. So the red pulse is the center of wherever the red is, right?
Uh, g of t minus tau
Yeah, no, I know, but
and f of t. Well, the whole.
what's the center of the red
Hold on, let
pulse?
me. Yeah, let's just read it
A
one more time.
snapshot of this
All right, snapshot
movie.
of this movie shows functions g of t minus tau
Uh-huh.
and
So
f of
the only thing
tau.
that can be
Okay,
possibly
for
be
some value
changing
t
is t. So t is changing,
is defined as the distance.
right?
Oh,
G of tau represents that red box. and t minus tau just represents
Yeah.
the moving of that box.
No, no, no. The red box is g of t minus tau, right?
Yes,
Oh,
yes.
g of tau
G,
represents just
G
the
of
red box
tau
at one
represents the
point.
red box, and t
Oh,
minus tau represents the moving of it because t is changing.
yeah.
Right? T is the x-axis. No.
Yeah, the last line says that the movie is created by continuously changing t
Yes, exactly.
Yes.
and recomputing the integral. Yeah.
Okay. And recomputing the integral.
Mm-hmm.
Okay, so
That's where it
okay.
goes down.
So so the result is a function of t, but is plotted on the same axis as tau for convenience and comparison. Okay. In this depiction, f of tau could represent the response of an RC circuit
Okay, I see
to
what
a
they're saying.
narrow
Hold on, hold on.
pulse.
Sorry. So what they're saying is that triangle that gets created really, I don't want to say it doesn't have to do with tau, but that
It's a
triangle,
it's a
it's a
function
function
of
of
t,
t.
but they put it here
Yeah, yeah,
just for
yeah, yeah,
convenience.
yeah, yeah.
Just on the tau graph for
Yeah,
convenience.
exactly, exactly.
Um, okay, I mean, if yeah, yeah. Okay, so I mean, this is RC circuit, a narrow pulse that occurs at tau equals 0. In other words, if g of tau equals delta tau, the result of convolution is just f of t. But when g of tau is the wider pulse, the response is a smeared version of f of t. It begins at t equals negative 0.5 because we define t as the distance from tau to the center of the wide pulse.
Is that saying
All
that
right,
it doesn't
I don't know.
move? Wait. In this depiction, f of tau could represent the response of a
That's where
circuit.
they start to overlap at point 0.5, negative point 0.5. They start to
At
overlap.
negative 0.5, they start to overlap.
Yeah.
Right. It begins there because yeah.
Yeah,
Um,
that's where the edge is. Yeah,
but
that's where they.
but I mean, it's obvious from the picture. The words are confusing me.
Yeah, the words are. If g of t equals delta, or g of tau equals delta tau, but what's delta tau?
So I think tau.
Is this just another function? The result is just f of t.
Well, if you scroll up, you get they show you delta tau. Yeah, in this one.
Oh, oh, uh,
In the yeah, delta tau is just f of tau. The function is the delta function, which gives you
Right, but they're
a
saying,
line like that.
but they're
That's what it's
saying,
supposed to.
they're saying delta tau is g of tau. So in other words, yeah. So like in the unit impulse one up there, they're saying if f of tau is delta tau, then you get g of t, right? But on the bottom one, they're saying if g
now
of
they're saying it's
tau
g
is
of tau.
right, if g of tau is delta tau, then you get f of t,
Okay, the
which is
result
sort
of
of
convolution.
reversed, and it's not
Yeah, it's like a
obvious to
reverse
me,
of a
but
similar thing. Yeah, that doesn't seem obvious.
Well, because one is a reflection of the other.
so what's interesting though,
So
okay, so here's something to definitely to think about. Once you get to
Smeared.
once you get to zero, it's smeared. Once you get to 0.5, there it's exactly the same. It's exactly the same as the original f of t function. Right? So once it gets to zero, once it gets to what do they call it? Defined as distance from the tau equals zero axis to the center of the wide pulse. It's got to have to do with that because once you get to 0.5 in this case, so at negative zero point
Oh,
0.5 to 0.5, there's
oh,
there's some overlap happening, but after that, it is because the entire g of t function
oh.
is passing through the other one. There is no like sort of like
Yeah, I see.
at
So
a certain point it becomes identical.
at a certain point, the convolution function is the same as f of t.
Right. So imagine the
Um,
diagram above.
but it's a smeared version of f of t because they're not exactly.
Well,
Oh, the same or something?
Yeah, yeah. Well, imagine the one above was much. The blue one
Yeah.
was much wider. You'd have a yellow box
Yeah.
for a much longer period of time. So for a longer period of time,
Yes.
you'd represent the f of t function. And as long as it didn't like completely,
Yes.
as long as it wasn't piecewise and didn't break away, you would have what you have on the bottom, where it's like goes perfectly in line with it. So assuming that
Yeah, I
goes
see.
on
Yeah, I see
forever,
it. These two. Yeah. Yeah, I hear you. So they're literally the exact same function.
they're the same function. The convolution is the
For a long
same as
time.
f of t. Yes, yes,
Yes.
exactly.
The other thing is
I think
the
that's the main point.
historical,
Yeah.
the
I gotta go to the
historical.
bathroom real quick.
Oh, okay, yeah. I was just gonna say the date of the creation is in like the 1700s. This existed before the standard normal distribution existed.
That's funny. That's actually
Yeah, so I would imagine this came out of the agony of trying to calculate distributions in some way or something like that. Because the problem with the standard normal distribution is you can only calculate like half of it symmetrically, you know?
What do you mean you can only do half of it? What does that mean?
Like you find the integral, I guess you could find the integral between 2 points, but isn't a cumulative standard normal distribution equation isn't that only for half of it?
I don't know what you mean exactly by half of it. I mean, you can so there so standard normal is the I'm assuming you mean the bell curve.
Standard deviation of 1, mean of 0.
Yeah, exactly. So like for example, but I forget the exact numbers. Maybe Shane, you better be able to actually. You spent a lot of money to know the answer to this question. So I
So
think,
you'd
but
say what, 68,
yes,
95,
exactly. I was gonna say 68, 95, 99, whatever it is.
99 points. I mean,
Yeah, yeah. So so one standard deviation away from the mean is, I think it's 68% of the population or whatever, right? It's like 68 and a half maybe, or 68
yeah.
something.
Yeah.
And
Yeah,
then
it's
and
yeah, I mean it's close, right? But it's called the 68, 95, 99.7 rule.
that's what it is.
Not
Okay, so two
exactly.
standard deviate between -2 and 2 is 95% of everything. And then three standard deviations is 99% of everything. So it's, what is it? 68, 95, 99, right? Is that what you said?
99
So
point
so
99.7.
so Michael,
Yeah,
to
let me just show you
to
like
your question, I wonder if you're thinking about p-values and stuff where you're sort of
What was
setting.
his
do
what
you
was
see
his
my
question?
screen?
Yeah,
I
why
wasn't
don't, yeah,
here.
I can see your, we can see your, can you ask?
So what I was
Shane
saying
was
is
at the bathroom, so if you
this
could.
okay, I was saying this equation for the convolutions came
Yeah.
about 300 years about 250 years before the invention of the standard normal distribution.
Wait, what do you mean
Yep.
250? When was Gauss around?
I mean, there were normal distributions, but the standard normal distribution came from like at the time of
Wait,
NASA. So it was sometime
time of who?
while NASA was around. NASA,
Not
because they were trying to
Gauss?
figure out.
Because Gauss did that right there. What you're highlighting is Gauss. It's a Gaussian distribute. Like, he did
Yeah,
that. So but that was also in the
but they're trying to
1700s.
figure out how to analyze. Well, they're trying to figure out how to. I mean, what I understand is, they were trying to figure out like properties of every normal distribution because I can vary standard deviation, I can vary mean in this equation. So what I was saying,
Hmm.
what year was this from?
17 something. Gauss
Oh,
is
that's not
like
his screen. I'm gonna look at John's screen. I was like, what are you?
Gauss is like
Yeah. So I mean, it's literally called a normal distribution. Is literally called Gaussian. Right.
hmm
That's just another name for
Or I was like
normal.
talking to somebody from
So
France, and they're called
I'm not
Gaussian.
familiar.
Gaussian.
If I took the integral of this function, it's only half of a bell curve,
If
right?
you took the integral of that function, you get one. If you went from negative infinity to infinity, you'd get one.
Negative. Yeah.
Okay, never mind then. So
I mean, I don't know what NASA did, so it's hard to like. I'm
they
not really
can't.
sure what they're.
Well, what was when was the
But like
stand?
that, just the normal distribution. Yes, that's Gaussian.
to see what year. Uh,
Yeah. Well,
History of the normal distribution. So what I was getting at is he's trying to reflect it and then calculate the area underneath.
that I agree with. The reflection
Yeah,
part, I totally agree with that. I
yeah,
mean, if you follow the history of this, like this talks about De Moivre, but it also so it's Bernoulli, De Moivre, Demois, whatever his name is. Yeah, binomial distributions, that kind of stuff. And you end and see it says De Moivre, Gauss. I don't exactly know how Laplace plays into this, but it's in the 1700s, right?
1809. 1809 developed the formula for the normal
Right. So it's
distribution. Yeah,
it's
yeah,
50, 55, 54 year whatever, 55 years after what we just looked at. So you are correct that the convolutions came first, and that I think is actually an
I'm just
important
off by because NASA did something different there.
off by 200 years. Yes.
Yeah, I
But
mean,
I think you're
But
right
I
though.
think everybody was trying to like figure out. Yeah,
I
everybody
mean,
was trying to figure out how to draw that normal distribution, and like that's basically, and this has an
maybe.
alternate use, but
Maybe. I mean, I don't actually see the connection to the normal distribution here yet, but I'm not against it
yeah,
because it is
I
within
think
the same time frame. So
it
yeah,
seemed. I mean, just from yeah, it seems to me that they, from like the most basic level of this, they just needed an integral to calculate like the area between two functions, right?
and
For
let's not
example,
forget
curve.
integration
And
itself
in
was
our
100 years
sim-
before that.
that's yeah, yeah. So that's kind of what I'm saying. It seemed like they just needed
yeah,
an integral here to get that. I'm sure there's a relation to the normal distribution. Uh, I don't know it though.
yeah. Well, you
Uh,
never really know, but you try to go back to the original thought that it probably had,
and what?
but
Yeah,
that kind of like leads you down the path of like what he was thinking. Why do I need this?
I
Instead of figuring
100%
it out.
agree with that
You know?
philosophy. I am a 1,000% agree with that philosophy that you need to go into what these people were thinking. You can't just accept some random thing that came later. I am complete agreement with that.
Yeah. Uh,
all right, so
So now that
let's
we
actually try
feel
and
like
do
we have some
some
intuition around this,
convolutions.
yeah. So I have the page loaded up,
Yeah.
Shane, as well.
So
If you need to look at it or whatever.
okay, I got it on one of my monitors. But I guess if you want to go through it, and I can just start. So I have
Sure, you
this
want me to like
DSP
read it out or whatever?
package, I guess.
Oh, really?
Yeah, do whatever.
What is DSP? Um, well,
I don't know,
first
but
of all,
so I
using
gotta install it.
using is
using
lowercase.
yeah, exactly. Using is also lowercase. That's one thing. But
Uh,
I don't
they
know.
messed that up in the book. That's all I'm saying.
They did? Oh, they did. Yeah.
Yeah,
Wow.
they did.
Um, that's funny. I mean, it's not really that funny. All right, let's see. I'm gonna use Bing for this. Let's see how Bing does.
Package.
You gotta using package too. You have to.
Oh, I gotta do using package.
No, 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 no.
Yeah.
Wait. What do you?
So it's
Oh
like
shit. Wait.
import package.
No, 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 no.
Or using.
Using package, like he
Well,
said.
it tells me right here.
Oh, it does say
Well, I
that
guess you
actually.
can use it.
I thought
Yeah,
you.
it's dude, hate it.
Yeah. No, but see, the thing is that in Jupiter you don't have like the REPL. You would just hit the hard, hard.
Yeah, the square bracket or
Exactly,
something.
the square
Something
bracket.
like that.
Yeah. So this package is called digital signal processing. That's what DSP stands for. And one of the things is convolution. They do estimation, filter design, window functions, utility functions, linear predictive coding, and periodogram estimation. Okay.
It's taking a minute to run just 'cause first time
Mm-hmm.
this package has been.
So I think from now on, you should be able to just do using DSP. Actually, I think you still have to run
Yeah,
that.
after.
All right, hang on. I'm gonna
Yeah,
go
I
get
do.
a drink. I will be right back.
Alright.
Yeah, I'll be right back too. I'll let this run for a sec. All right. Looks like it's almost done.
Yeah. But what I was saying is NASA did something. Somebody was telling me about this, where like NASA, I guess well this is something I'll tell you. NASA was calculating all the they you have the normal distribution function, but you don't know to set the mean at one. I mean the mean at zero and standard deviation at one.
Yeah.
What they were doing is calculating all the possible standard normal distributions, and
Yeah,
then
yeah, yeah.
and then eventually they said let's like set the benchmark as mean of zero, standard deviation of one. From it. I mean that's
I kind of see. Yeah, that sounds okay. Yeah,
and
that's
they
cool.
were really struggling because there's actually multiple equations for like one is based off of the circle that you end up using pi. There's like multiple equations where they were
Yeah.
trying to draw it too. So there's other ways of estimating a standard normal distribution.
Cool. Yeah, I didn't know that. That's sick. I'll check that out. All right.
Yeah.
So now I'm mute.
Okay, I'm back. Shane, you broke everything. It looks good.
We
It's
got
those are just
no,
warnings or
bro.
whatever. It's
Remember
all good.
Julia?
I know.
And,
Now it's building it.
and,
I wish they
and
wouldn't
Julia
use.
Red is good.
What's that?
Something
Dawn, is
like
this red or pink? Do you think? Because I think it might be pink. What do you think?
that.
Dawn says pink. See, it's not red. If it was red, that would be
I call it light red.
light red. Okay. Which is by definition pink, Dawn says.
Yeah. Yeah.
Okay.
Tomato.
Tomato, tomato, he says, Donnie. That's a good one. That's actually appropriate, funny enough. Um, I think you needed a lot of tools, it looks like there, you know. Like you've never used polynomials apparently. Some reason it needs XML. I have no idea why.
There's
It,
a lot of
I've used that easy
Oh,
XML.
these.
I've used the easy XML package actually. I've used that one. Funny enough. Polynomials though, that could be really
yeah, but
useful.
the question is like
Iter tools.
Well, that one seems like a standard almost.
have you
Iter
guys
tools.
heard of those security scanners that exist? I was
No.
like, what if one of these packages has like a security issue in it? You know?
Well, I don't know what Julia does, but when Python or Node or JavaScript have that issue, you'll in the package manager will notify you. Well, it won't notify you, but when you try to run a different package thing, like for Node.js, it'll say, "Oh, some of these have security issues" or something like that. You know what I mean? And the only way that they would know that is if there are issues on their Git page or something like that. I really don't know the Julia package manager well enough to answer that question. But I guess the answer would be like, how does it even know that there are security issues? If you can answer that question, you'll probably lead
Well,
you to.
this is a feature that I think Microsoft, because they own GitHub, should do. There's a lot of open source and paid vulnerability scanners. So what you do is after
Right.
you write your code, you scan it for vulnerabilities
Right.
automatically. But like,
Right.
if Microsoft did it because they own GitHub, it would be an amazing feature, and I would pay for it. Wouldn't that be awesome?
If
They were
if
like, we went through all of the code.
Well, what I know about
dude,
what I
that's a
know about
lot of
that
code,
is
man.
A long time ago, when I posted some secret keys to GitHub,
Yeah.
I got an email from Microsoft.
From
or GitHub,
Microsoft.
and they were like,
Wait, from
I got an
Microsoft.
email from
Microsoft didn't
GitHub.
own GitHub when you did that. You're talking about a Chrome?
Okay, yeah, yeah. So not Microsoft. I got an email from GitHub that said, yeah, you might want to take that down. So I did.
Yeah,
It was
but
too late.
yeah, exactly, Michael. So before I got to this company, Shane was like one of the first people working on AWS, and one of the things that AWS is like. So first of all, it's not totally Shane's fault. So like the company didn't know what they're doing, and they gave him like some intern access to the root account, and so he to make his life easier,
Everything.
he had his security. He had a access token or access secret key and a token, whatever. And we've learned how you.
They didn't even have repos set up, by the way. Like they didn't have
Oh well,
any
that
type of
see like
none of
yeah,
that.
yeah.
Yeah,
You'd almost have to have
stuff
been
like
an
that.
expert to avoid this situation. Honestly, this was like an inevitable. If they didn't have repos, they didn't have nothing.
They didn't have
So what
anything.
happened,
Yeah.
Michael, was Shane hard coded these things into his repo. So if there were no repos, you went on GitHub. So you put it in a public repo. You put the company's access key and secret key in there. Then somebody had a like a crawler was crawling GitHub repos because that makes sense, and he was searching for access keys, and he probably was doing it for more than AWS, but he did it for
And
AWS, and then it automatically started spinning off EC2 instances, which are computable clusters, and he started mining bitcoins. And in one night,
and they maxed it out.
one
They
night,
maxed out like the number of
yeah, they would
bitcoins you could
just.
get
It's
up to.
probably like a infinite loop until you can't do it anymore, until they hit an error. And he caused in one night $20,000 worth of damage in a single night.
Oh wow.
Yeah.
Well,
So
I've seen worse. Like
I'm,
when I worked for that electricity company I used to work for, they would drop batches, and batches are like $1 million each. So they would like get dropped in the EDI transactions, and we'd
what's
find
a
out
what's an
like that
EDI transaction?
electrical data interchange. So there's already a standard in place for companies to talk to each other digitally and do all their accounting. So like EDI is a standard that they created to eliminate a lot of paper transactions.
Mm,
But what happens if you're billing your customers and then one of those they process them in batches usually. So what happens if a batch gets dropped? Then you lose like all this data that should have been paper trail. That
I
should have
see.
existed. You might
I
end
see.
up not billing like $1 million to customers. So we used to find these drop batches, and then like it was like a major fine to the
Do
system,
they
like
have they
$1 million.
moved at all to like blockchain because of that, or is that even part of the?
No, EDI is like there's like centralized providers, but they're all like on the cloud pretty much, or they have internal servers. Because the thing with EDI is you have to have essentially zero downtime.
Oh well, okay. Well, if that's the
Like it
case,
has to.
so not only do you have
If
to
you
have
go
zero
down for like a
downtime,
minute, you drop batches of
right? But
files.
but but the problem is, okay. So there's a concept called soft real time. So soft real time means if you drop packets, it might be okay because eventually the system will get back to where it was. But if you have a hard real time situation, like it sounds like what EDI is, which makes sense, it's money exchanges, whatever.
Yeah,
Then you are going to be in a then it's that's like very difficult because now you're in a situation where you say, well, we can't afford to drop any packets, and we need it to be in real time. That is the hardest thing in the world to do. You can't. I mean,
well, also the really inconvenient part of it is all the systems are designed as pull systems. So you have the utility company, the EDI goes to the billing, the EDI provider, and then it goes to the res, and it's also being reported to the LDC and the settlements company. So if you have an error that occurs in one of those files upstream of you, it just gets absorbed into all the
you
systems.
get compounded. Yeah, yeah,
Yeah, and so like I was dealing with errors, like because everybody's designed to handle it dynamically. I was dealing with errors like companies that I didn't even cause, and you have to
yeah.
figure out how to error handle it.
Geo, Shane, you know what that's like, right? Not quite at that level, but we have these
uh,
actuaries who are don't know. They constantly causing errors.
oh yeah. I was
Hey, fix my error. Except they asking
yeah,
him to fix it.
in like Excel. They're like,
Yeah,
Yeah.
you've done something with a computer once, haven't you? Oh,
yeah. I
here.
plugged
Well,
my Xbox in.
actuaries are really like
Yeah, my
low.
fix my fridge.
Yeah,
Uh,
actuaries are like low tech people.
Oh
They
my
do nothing.
God, yeah.
Yeah.
Shane also made a evolutionary biological statement about them and said that they are born with a specific pattern of like DNA or whatever. He called he you know, for layman's terms, he called it the boring gene. But I'm not sure that, you know, I'm not sure that that's official. But
We
it
need to do a proper study.
but he
So we're
there's a high correlation, or if the functions are the same, then a convolution apparently to these things. See, I'm trying to bring it back here.
yeah, no, that's good. Yeah, there's a correlation is the hypothesis. So
Well, like an almost perfect correlation. That's the. All right, what did you find there, Shane? Because that's different than the book, by the way.
yes, so that's what I was gonna bring up. So I got a different. So I mean, I just used the function. I did DSP dot too and got the same thing. But all I did was just the convolution of the convolution and got
Hold on,
something
let's
different.
let's let's go through it. So you have A, B, and C, and
Yeah.
so can you do the convolution of AB? Can we just look at that? So AB should be yeah. Let's take a look at what this actually returns. Maybe it returns something fucked up. All right, so the AB. So let's think about what this should be though.
You have a different number of elements in your array too. They have
What?
six and you have seven. He has seven and they have six.
Oh, that's true too.
Oh, yeah. Okay. So let's talk about this. So let's start it with convolution of AB. Let's figure this out. So we have x squared plus x minus 2 times x plus 1, right? So this is AB.
Yes.
So it's oh wait, it's not even. Oh, really? It goes like in that order? Maybe it's backwards. Maybe that's why.
Well, oh yeah, that's a good idea. Let's try something. But at the same time, we're actually built. The next step is to build out our own convolution function. So I'm
Well, you
not.
would need to do BA. No, no, no. I didn't mean convolve it backwards. I meant literally it's backwards, possibly. Like in other words,
Like this is. Yeah. What do you mean?
so in other words, 1 negative 1. Can you make like an E? Just make an
Yeah.
E real quick. And an F maybe. So an E would be 1 negative 1 and 2. And then can you make an F? And then F would be negative 2 1 1. And then do convolution of A E, or convolution of the convolution of A E comma F.
Convolution of the
Yeah, yeah. Just change. No, no,
convolution
no, no. Yeah,
of
yeah, 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 yeah. A E
the.
and then F. Yeah, do that. Damn it. All right, I have no idea. So
Well, we build it out though. Like our next step is to write the actual function. I think.
All right, let's do it.
something's wrong though. I mean,
No, the next step is the Toeplitz function.
Oh.
yeah,
Okay.
like
Not
I
actually.
would want to figure this out. So you end up with two. So you end up with the original function plus x times the original function. So you end up with that function plus 2x. I need to do this. Hold on. Let me get Wolfram real quick. Let me just. Oh shit! I don't have it on this computer.
Oh yeah, well, framework.
Yeah. What?
Wolfram
Can you
Alpha.
do that in Wolfram Alpha? Yeah. Can you just while you have it on the screen, can you just put that in Wolfram Alpha real quick? Just do the
You have
product
to
that.
kind of help me with the syntax here.
There's no real. Yeah. There's no
I
real
know there's not really
syntax.
syntax, but do
Just
I say
just
They
like
give you the equation.
just
You
do the
can
first.
calculate.
Just do the first two, Shane. Just do 1 plus x times 2 minus x plus x squared. Do that.
okay, 1 plus x,
Yeah, but you probably need
what?
the paren, honestly.
1 plus x.
Okay, and then do
Times.
another paren. Yeah, you don't even need the times, but let's do 2 minus x plus x squared. And we want to see if the convolution of AB is equivalent to this, because something's wrong, obviously. Is that a 2? Wait, what is that? 2 minus x? Is that what that was?
Yeah, 2 minus x plus x squared. Isn't that what it
Okay,
means?
yeah. Can we see what it said? What do we get? Wait, hold on. I can't see it. Can you go to the Wolfram? Let's just find because we're looking for. Okay. Can you? Sorry. Can you make Wolfram Alpha bigger so we can actually look at it? Okay. Um, Scroll all the way up for a sec.
Indefinite integral. Is
Yeah,
that
yeah,
what
but
you're talking
scroll
about?
just scroll up. All right. So it's x squared plus x plus 2, x squared plus x plus 2. So the convolution, yeah, it's the second one. Wait a minute. Oh, x cubed plus x plus 2. So it should have 4. So it should be 1012 or 2101. One of those. What is the convolution of AB? It's not even close. It should have 4 of them. I don't know how it gets 5.
That's the reason why I think the function is
Wait, what
broken.
is CONV? Maybe can you just do a question mark CONV, and then can you maybe do DSP dot CONV and try that because I don't even know what.
Yeah, I did. I tried DSP when.
No, oh
Um.
DSP.
Yeah, I tried it,
Can you
but we can do
wait?
that
It doesn't
too.
say a convolution of two arrays. A convolution of the matrix A with a 2D separable kernel generated with two vectors.
This actually is a different one. Oh no, it's not.
Just do that one. Just to make sure. I'm sure it's the same. But also there was a CONV2, which I don't know what that meant. Something's wrong.
That takes in a matrix. Oh no.
Mm-mm.
Uh,
It was literally a different function. That's just right there. Is just it's the same function. It's what do
the
they call
user
it?
amount there right
Multiple
here.
dispatch. Yeah. CONV2. See that? How you search for it? I don't know what it does. I don't even know if it's.
Deprecated.
Oh, thanks. Okay. What? You you know what though? I think Michael's actually right when he was pointing out that there was two more elements. I wonder. Let me see. 1, 2, 3, 4, 5, 6 elements. You know what?
Matrix.
Actually, let's do this. I got an idea. Can you try this? So,
Yeah.
so do the regular convolution that you have here. Let's take a look at this. I have a guess at what's going on.
Okay.
So, what's the regular convolution? The A, B, C, whatever it was.
Down here.
What's the
Got it.
okay? So can you? I'm sorry to ask you this, but can you do? Let's see, how many are there? 7. So can you do 4? Plus negative 7x squared plus 11x cubed plus negative 11 to the fourth power x to the fourth power plus 5x to the fifth plus negative 2x to the sixth into Wolfram alpha.
Wolfram alpha alpha.
And then
Yeah.
plot the original one that we were supposed to get. And I'm just curious if those two functions are almost identical.
Yeah. So. Okay.
It should be the coefficients that it gives you.
Yeah, yeah, you have to use them as coefficients. So the only one that's missing is the x to the first. So all the other ones, 0,
Squared
1,
of
2, 3.
11x to the third plus minus 11.
If it's whacked out, then we don't know what's going on. I'm going to look at.
Plus 5x to the fifth minus 2x to the sixth. 2x to the sixth.
Yeah, you're not sharing, by the
I
way.
think I think the calculation on the book is right, but I don't think the.
Well, the
I think that
calculation on the book almost has to be right because they literally wrote the algebra out for us.
Yeah,
Right.
exactly.
So it's like, yeah, I agree with you on that one. Um, their axes must be a unit, right? Yeah, it's fine.
So this definitely isn't the same function.
Well, see if you can write convolution.
Yeah, I tried that too. I tried just doing like this. Oh, but I might be just doing it like John. If
Well,
Wolfram Alpha wouldn't
that's
be able to do something like
you would need
that,
to have
right?
two functions.
So I would need to say 1 plus x.
You would need to have the function. You're literally just writing the coefficients, and it doesn't know that that's what you're trying to do.
Yeah, so this would be like 2 minus x plus x squared. Like that.
Yeah, something like that. So actually, there is a
Um,
Wolfram Alpha. Somebody made a widget in Wolfram Alpha to do this. Let me. I'll send it to you.
Okay, so we got something here.
Oh yeah, you got it. That's what it is.
So what is this? So what is this? This is 1. Yeah, how do we interpret this?
Is there an
This is
equal sign in there? I can't even see it.
there's no equal sign in here.
It's freaking terrible. Here, let me send this to you real quick, and if this doesn't work, we'll just I don't know.
Well,
I sent you something, Shane.
on Facebook or
No, on the chat here.
okay.
Or you can type in Wolfram Alpha. It looks like you can just type in convolution of two functions.
Okay. Yeah, let's do that.
Yeah, just type in convolution of two functions. Yeah, you see?
Okay. And then what a here is
Well, open
1, 1,
it
and
up
b
and
is 2,
then
negative 1, 1.
yeah. There you go.
So 1 plus x, second convolution function, is 2 minus x plus x squared, I think.
Yeah, and then the
Is that
result
right?
of this is what we need to convolve against C and see what Wolfram comes up with. You're good. I think that's good.
You might want to send him an email about this one because this is like the worst.
Oh, it came up with the same thing.
But okay.
I don't know what
But
the transform.
we don't have a way of verifying like what the convolution besides
I
doing.
would just send them a question. You know what I mean? You might
We
get
could
into
really
Stanford
quick
with grad school.
in Wolfram Alpha. We can really quick try and do. Well, you can't do the convolution of the convolution.
Yeah, you can. Take the result and do a convolution of that.
So do a convolution of that. Oh, that's in freaking image, dude.
Look, what does it say? F of x, g of x, y gives a convolution with respect to x of the expressions.
Uh, here, let's try this. 1 plus x, 2 minus x plus x squared, and then just real quick, and then maybe we can go on to the next part.
You can also type simplify in front of that, and it'll simplify the whole thing.
Yeah, that's true.
And what is c?
Um, hold on, I'll get it for
C
you.
is 1, 1, negative 2.
Yeah. 1 plus x minus 2x squared.
So let's just double check this. So we have a and b. So a is 1 plus x, 2 minus x plus x squared.
Mm-hmm.
And then
Yeah, you're right.
C is 1. Okay.
Yeah, that's definitely how you do it.
Wow.
You piece of
Never seen a
crap.
nicer formula.
Well, it didn't do anything. It just
Yeah. Didn't do
I think the
anything.
problem has to do with something about what they said, like transformation stuff. I don't really know. That's unfortunate, man. After adding this package, the command can be used to compute the convolution of vectors a and b. It didn't work though. Why did it come
I
up
think
with
that
the?
function is broken. I think it's broken.
All right. Well, if you think that, let's go. Let's go to. Can you go to the DSP GitHub page, Shane? Or do you want me to do it?
Yeah.
And go to the issues
You want-
and look up.
It's for Julia.
Yeah, but you got to find the pack. Wait, this is not the package.
Yeah, no,
Sorry. So the package,
it's this, right?
that one, yeah, yeah. I'm assuming that's it. There's one below it too. Actually, can you go back for a second, just real quick? There's one below it. What's that?
They're
Oh,
both
it's gonna
show
have
DSP.
DSP.j. Okay, fine. Yeah, yeah. All right. So look at the yeah. Anything say convolution? Look up convolution somewhere in the repo.
This conv right here.
Yeah.
When performing similar convolutions, it would. Well, it would be convenient.
See, here's the thing, man. These people don't think there's a problem. So wait, scroll down. Use overlap save algorithm for con. What does that mean? Um,
Yeah,
Then
it's the most.
cite the book and cite the
oh, so you can
screenshot.
wait a minute. Wait a minute. It's overlap save. Okay, okay, okay. So you can use two different methods here. Um. Okay, I think because we're using FFT, I don't know if that's the right thing. We probably should be. Hold on, I'm trying to find it. You. How do you tell it which one to do? They all
Their
take
access.
they all take in two though. All the convolution ones take in two. You can use either FFT or overlap save. How do you pick one? I don't know.
It depends on the size of the size of the array.
Use either FFT or overlap save depending on the size of the input.
Oh,
U and V can be n-dimensional with arbitrary indexing offsets, but their axes must be a unit range. Oh,
well, all right. So we can also be. I don't know how much time you guys want to waste on this, but we can also be smarter than them. Not likely, but we can actually make this work. So how would you write? I know you guys gonna hate this, but how would you write the matrix to get the results that we're trying to do? Because we're literally multiplying the
like
we're what?
I was saying, wait, are we sure that the next part? I didn't read really too much about the next part here, but isn't it doing it in another
It doesn't look like it. It's doing a different function.
Toeplitz matrix and check it against the conv function? It says. We will also check that Julia is using the very efficient method for computing the convolution.
Okay.
So this matrix, you end up.
It's
getting
gonna
the
be
same
wrong
result.
though. I mean,
TV times A and then convolution. Yeah. So I mean, I don't know. I think we should. This part's not going to be wrong. This
what?
part we'll see what the convolution is, right?
Yeah,
You
but
see
there's no
how?
checking, and there's no checking of what
Yeah,
time.
there is checking.
It's going to
If
be
your
wrong.
TV times. Uh, oh, it's going to be different, is what you're saying.
Which
Because
is
we have
literally wrong.
Yeah,
Yeah.
yeah. Okay.
What Julia
But this
version
is
do you
one.
have, by the way?
This is one way to do it, though. I guess. So
I mean, well, we're not doing it though. We're skipping it.
Let's just keep going.
What version of Julia do you have?
1.4.2.
Ah, so do I. All right. You got 1.4.2. I have 1.4.0.
Yeah, me too.
Yeah.
It's that package.
Well, we're
so,
skipping
Yeah.
this function, but we're still calculating the convolution, right?
See, even if there was an error in their
That's the-
code,
that's-
these guys wouldn't know it because they're probably not.
No, they're just using an alternate package, you know. But honestly, like, I mean, we can move it. We can skip it for now. I personally, I feel like doing a convolution if it's literally just multiplying two functions together. I feel like we should be able to do that. We're smart enough to be able to figure out how to do that. Like
But
because you're
it's not just multiplying two functions together, right?
Well, the
Um,
thing, the way that I envision checking this, because it's the easiest way to check it, is the number of elements. So
yeah,
if
no,
you have to,
that's correct. That's
no,
correct.
that's like
But
yeah,
wait a
that's
minute, wait a minute, Shane. What do you mean it's not just multiplying them together?
well, you have two functions that you're multiplying together, but then you also find the integral at each point of t, right? As well, it's not just the multiplication of the two functions; it's the multiplication and the integral at each point that they overlap.
Hmm. So you
So
find
it is a
you
more
you
complicated
find the
one.
multiplication, right? So you do, yeah, yeah, gotcha. Because you,
Yeah, I mean, I'm fine. I'm fine to do that, but I feel like we
no,
could
you're right.
probably.
I thought it was just the multiplic. If it was just the multiplication, but now based on what you
That's
just
gonna take
said,
a while, though. It is a more complicated
well,
one.
it's not much more than that, but it is more. I thought because what you'd have to do is just, I guess, take a lot of discrete steps
Yeah,
and
you
sort
could
of
probably
sum
do it
them
in a
up.
several ways. You
There's
could
probably
probably do it in
several
an
ways to
integral
do it. Yeah,
package,
exactly.
but like you said, you could also do like the Raymond, like or like kind of method out of just like breaking it down to really small discrete
I
steps
mean, that's the
and
naive
then
way to do it,
adding them
right? That's
together.
the way that, as Michael would say, that's the way they thought of
This also,
first.
yeah, and there's also probably an integral package that we could use to do
Yeah,
it
I know.
in the end.
I'm with you.
Um,
I missed a step.
well, I'd be down to like after this. We can
On
set up a
our
Google
own,
Summit
I would
after this
say do that
session.
on our own.
I'd be
It's
down
just
to
a
play
little
around with this
annoying that it's
and
not.
see what we come up with. Yeah, I agree with that for sure.
Hmm.
Um, but I mean, we didn't do anything wrong here. We're literally using the same function. We're getting the wrong result or a different kind of convolution or some shit. We don't really know, but
Oh, great! This was made for kids.
yeah,
Now
that's the
I
reason
have to
why I was
change it.
saying
oh,
I think you should send whoever wrote the book a message to see whether.
I would want.
No,
Yeah,
I
I mean, I
agree
would
with
want to
that.
kind of dive into it
I
first,
don't
and
disagree with
then
that. Yeah, I would want to dive into it
Because one
first.
of the two of them is wrong. Either they're doing it wrong, or the code is wrong.
It's hard to
And neither
believe
one of them knows
the
that.
book seems right though. You know what I mean? And it's impossible to tell from the Wolfram Alpha thing what they even came up with, because they had like transformation variable and other variable, and it was like, wait, what? It made me realize I don't know it well enough.
yeah, that's what I was like you pointed out. There's two different. There's probably a couple different ways to do convolutions or whatever, and I guess that's what
Well, let's not
I don't know.
forget
They
that
had
those
those.
videos that Khan made, and then the other guy switched it completely, and like
I forget what they switched. Oh,
he
they switched like the
the
variables or the
functions, yeah.
functions.
I was like, wait, what? It wasn't obvious to me
Yeah.
like how that worked.
Well, and even our insight in the beginning, even though it makes more sense, you could reverse the integral and go from infinity to negative infinity, and then make it
Mm.
move right to left.
Mm-hmm.
I'm sure
Yeah,
the
yeah, yeah,
results.
yeah.
All right, so we're writing. If I remember correctly, the Toeplitz matrix, it basically does the convolution, but it's a special matrix that will do you can multiply just by the matrix and you get the convolution. Um, so we can go through.
It's crazy.
and
Julia
analyze this.
totally allows you to do crazy shorthand calculation stuff. I'm like looking at the way they wrote this function. It's just like, it's crazy.
Yeah.
Oh, it's great. I mean, I love it. I think it's amazing. Like, I think it's like really impressive. You
Someone wanna read
you skipped. So you want to return t. Yeah. Okay. Sorry, I didn't see that.
All right. Do we want it? Someone want to read this?
The what? The what it says in the Julia.
Toeplitz.
Okay.
Yes.
So let's write a function that creates a Toeplitz matrix. Check it against the con function. We will also check that Julia is using the very efficient. So we'll make sure that Julia is using the most efficient one for actually doing the convolution. So to construct this matrix, defined in equation 7.3, Let me just pull that up real quick. I know that's
Yeah.
too much, but let me just do it anyway.
No, we gotta see it.
Right.
Yeah.
All right. So I think I'm
It's like
sharing, right?
it's sparse or something. It says you start with a 0 matrix.
0. Oh well, they always see that seems like a common thing. They always start with some sort of 0.
And then add to it. Change the
Right.
elements.
So what did they say? So
7, 3.
in equation 7, yeah. So but sometimes there's like figure 7 3 equation. All right. So there's the figure. Where's the equation?
Where's our toplets, though? Well,
That's
see the matrix. It's gonna be in.
I mean, I'm just going into convolution because
Yeah, it's gotta be. Oh, okay. That's kind of. Oh, you
what?
gotta scroll up to the T.
What?
You passed the toplets
I
matrix
did.
somewhere. I just saw it.
You
Yeah,
did.
that's it, right?
Woo!
Scroll down. You just
All
have
right.
it.
Okay. Oh
Yeah,
yeah.
yeah.
Okay. So these are toplets matrices. Okay. So let's see.
Oh yes.
This is the convolution formula. Wait. It
Yeah.
follows that which agrees with the convolution formula. Oh, here it is.
Yeah,
It's
it
this
should
one.
be
It's right here.
exactly equal.
It's that.
Yeah.
If you take TB conjugate.
Okay, so wait, let's just talk about it. Convolution is asymmetric. We have that a times b is equal to b times a. It's associative, the associative property. We can write both as just multiply them all. So one of them being 0 implies that either is 0. I don't remember reading this. I think you guys did. The two polynomials p and q and p are the same. Since multiplication are okay. Basic property of convolution: a times b is a linear function of b for fixed b. It is a linear. This means you can express a and b as a matrix product of the toplets. Matrix b times a equals the toplets matrix of a times b. Or t of b times a is the same as t of a times b, where t of b.
This is kind of like a common approach that this book has used, which I
It's
like
a
a lot.
suboptimal.
You can multiply. It creates a matrix for you that literally does the function
Yeah.
just by multiplying it.
Well, isn't that the
Properties
point?
of this matrix looks. Yeah, that's the point, right?
The fact that they can turn these functions into matrices. I mean, it seems like that's pretty.
Yeah. A huge, yeah.
All right, so yeah.
And this one has a special name, I guess. So this is interesting. So it's across the diagonals. You end up having the non-zeros. So b I minus j plus 1 for.
So
So you,
on B 1, 2,
Give
and
you a
3.
new A and B.
What?
Oh, they give you new matrices and vectors.
Mm-hmm.
so the first row you start the b1 diagonal. The second row you start the b2 diagonal.
Oh, this is what I actually. Okay, this is what I was actually trying to come up with when I was thinking of the convolution thing. I would actually have eventually have come up with this, because these are the coefficients, right? Or are they not? What's B1? What's B2? What's B3?
Yeah, oh, so they're. Yeah, I guess they are the coefficients because it's the vector. It's just the vector b that you're convoluting, which is the coefficients.
Yeah, and the constant.
They are the
is
coefficients.
The first one.
So that's
Yeah,
that's
you're
what this is eventually what I think
two
I would have
vectors.
come up with if I kept us down that path that we were talking about.
Except much faster.
Yeah, well, yeah, much faster. Okay, auto.
So okay, yeah. So this is okay. So I think we understand how it's made. Yeah, and it makes sense too. If you guys remember like when it was like finding all when we first brought up convolution in the beginning of this text, it find between two vectors, not even the matrices, it shows every single building up to every single combination, and then building back
Yes.
down.
Yes.
So that's I feel like that's kind of easy to visualize with this. Um,
I mean, this I don't know if this is where you're getting at, but this part did sort of remind me of that. This b
yeah.
minus
So
a plus b minus I minus j plus 1 part did remind me of every combination. But I mean, okay, so what you're saying, Shane, um, is is exactly
well, it's the
right,
same thing.
but it's
It's
almost
the same
not.
thing, yeah.
It's almost not that
Because
surprising because when you multiply two polynomials together, that's what happens.
yeah, that's what you get is
You're literally finding every combination. So if I take the first element of one, I need to multiply that first element by every other one.
yeah, yeah, yeah,
So you're finding the
yeah.
combinations of them all.
But
So it's
it,
not
yeah,
really
yeah,
that
yeah.
surprising, but it is. You're correct.
No.
I think you're
It's a good,
correct.
yeah, it's a good, I mean, it's literally doing the same thing, actually. If you just look at each row individually, first you only have B1, then you have B2, B1, then you have B3, B2, B1, and then it starts to build back down. Um,
Right,
so
right, right.
very similar
So for
pattern.
example, I think to summarize what you're saying, so B1 times this A1 through A4 or whatever.
Yes,
And then B1 and B2 times all that,
yes,
each one of those
yes.
with some offset, and then all of them, and then you start saying, well, what if I, right, exactly, what if I put
And then
multiple ones together? What do I get? And then I put,
to loop it back to your point about the two polynomials being multiplied together, that's like the multiplying the two rows by each other, and then you get the fullest version, like the biggest, most
that. Oh,
terms you could
sorry, that's
have.
what I meant. That's what I
Yeah,
meant. Yeah.
exactly. And you
You
gotta
get what I'm saying? You get the fullest version, but then there's all the other combinations to build up to that,
You
to
know
build back
what's
down.
interesting about so if we look at this, I mean this is quite interesting because like look at this Toeplitz matrix of the B vectors, right? So you see the B1, the
Yeah.
B2, and the B3. It's almost like obvious, like so how you would come up with this. I guess it's not obvious, but because it's one more than the length of the B's. But in this one, it's kind of the opposite, right? Because it's like one shorter than their actual length.
Well, you have four elements, right? In A. In the second one, you
You
only have
have
three elements.
4 by 3. Yeah, exactly.
so you gotta take the greater of the two then.
Well,
You have
yeah,
four
but
by three.
but this but this matrix has different dimensions. So it's giving the dimensions to the other matrix. You know what I'm saying? Like so the B matrix is the columns are the length of A, and the A matrix the columns
Mm.
are the length of B.
Yeah, yeah, yeah. And that also follows with like matrix like multiplication rules, because
That
you're
follows the
you're going by this
rules.
thing.
It follows the rules, but it still doesn't explain it fully, I don't think.
No, 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 it doesn't. Yeah, that is interesting, and the fact you can also just switch them around, I guess.
Right. So then if you do the associate right, exactly. Actually that's very important because if you do the wait a minute. Wait a minute. So we're saying T of A yeah, so this is what you're talking about, right?
Yeah,
So T of B times A is equal to T of A.
times B. So no, yeah. So
Yeah,
yeah,
but
yeah.
it
I
but
mean,
it
we are
oh, I
touching.
get it. Oh, wow,
Yeah, we
okay.
are we are touching on it. We are right. Even with the matrix multiplication rules, because like you just said, like T of A, you need to multiply
Well,
by B, and
well,
T
the
of B, you need
point
to multiply
is
by
to
A.
me that T of A and T of B are very different things.
Yes.
And
Yes.
you're basically just creating arithmetically the same situation. So you're saying what
Yes.
matrix would create the same situation?
Yeah.
Yeah.
Exactly.
So this is correct. This is not
And it's a very, very okay.
the
It's a
craziest thing
very
about
special
linear
thing.
algebra is to me so far is that everything is like very basic, but the complexity that are like the intuition and the complexity that comes out of it is like
Yeah.
not something you would guess at. Like so
Like
you look at calculus and you go, no, that requires some pretty creative, interesting thinking. You have to think in different dimensions on
no,
how this would work.
it,
But in this, it's like, well, actually, you
it's actually
don't.
pretty fundamental
It's actually
stuff.
pretty
You
fundamental, and then once you just realize it, you realize it. But it
In
and it
calc, you
creates
almost need to
complexity, but
you almost need to build up and have this, like, you have to keep building up, and you can't really forget stuff from like your previous understanding of calc. Here, like, you can almost show complicated linear algebra to some extent to someone who hasn't seen it, and they could kind of understand what's
right,
going
like
on
so
here. But
linear algebra people are like actuaries and the other people are like artists. Sorry. It didn't.
yeah, I don't know if I fully get
Oh,
what I was
what I'm saying is this one can be built off of fundamental things where the other one
oh
requires some sort of creative perspective. Um, that's just because I drank. I'm drinking a beer right now, and I apologize for the stupidity right there. But
no, yeah, no, I mean, this is a
obviously, I
good
shouldn't be a stand-up comedian.
this is good
Oh,
though,
so here's
because
the thing about an actuary. People be like, "What the hell's an
half of them,
actuary?"
they won't even know what an actuary
Yeah,
is.
exactly.
uh,
You guys ever
yeah,
work
so
on a spreadsheet? No, no, we haven't. But
my
or,
buddy, when my buddy graduated, he got a book like actuary jokes or something, and it was so bad. Like,
honestly,
that's all we give him.
the best book in that situation would be a book that's like maybe 150 pages that are all blank, and maybe that's it.
Dude, they were the
Wouldn't
worst.
that
They
be
were
the
the
best
worst
joke?
jokes.
Wouldn't that be better?
If they were, yeah, that would be one better joke than any of the hundreds that Waterloo gave him in the book.
So look at
But
my
anyway,
screen for a second. You can check the dimensions like this.
So just to point out, oh, I see your screen. Okay, great, excellent. Sorry.
Yeah. Suppose A is an M by N matrix and B is a P by Q matrix. You
yeah.
take N plus P minus 1 and N plus Q minus 1, and that gives you the dimensions of the resulting matrix.
Can you just pause for a second?
So that's
I
the
need to.
easy,
I need
that's the
to.
easiest check.
I need to. Yeah, yeah. I just need to absorb that because I know that you have no problem, Michael, with memorizing things. It is a major problem for me. So I need to.
I used to be like that too until I had a psychotic episode.
Yeah, that is not.
Anyway,
I hope not in the
yeah, that's
cards.
bad.
It's not a strategy of mine. So I'm going to
Yeah, don't do
hold on.
that.
Just give me a second here. So okay. So
So it's the rows added together minus one,
thank you.
and the
Yeah.
columns added together minus one.
So you end up with a new
Um,
matrix of the rows and the columns added together less one on each dimension.
Yeah.
I don't really. Let's see. It has a.
does that make sense with like all the combinations going on? Why?
So let's think
Why is
about it.
them
Well,
added together?
let's think about it for a second. So, well, first of all, what are the rows? What are the columns? So, so the rows. Okay, so if we look at the Toeplitz matrix, the rows are something like, is basically like how many like is a single combination, right? So the rows is a single combination. So for
Yeah.
example, so
Yeah,
for
single combination.
right, so like if in the B1 case, if we multiply that by something else, we're going to get all the situations where B1 interacts with anything else. And then in the other case, we're going to get all the situations where uh, B B2 and B1 interact with everything else. Okay, so on and so forth. So so the result of that being multiplied would be the amount of combinations that would happen. So the amount of combinations has got to be the amount of rows, and the columns have to be sort
But
of. Go ahead. Go
but
ahead.
what he's
No,
showing
please.
us is the dimensions of the convolution. It's not the
I
dimensions
know
of the
that.
Toeplitz.
I know
Okay.
that, and it sounded like what you said to me was, or what you said to us was that, uh, like if you multiply these two polynomials together, it's going to
Yeah.
show you what, what.
The maximum number of terms combined or whatever. I worded it something like that.
It's like the largest form of the possible combinations, right? Because that's going to have the maximum terms when you multiply the full two polynomials together. That's the overlap. That's like in Wikipedia when the first square function completely overlapped the second square function.
What do you say the maximum? What do you mean the
Um,
maximum?
so if you had, do you have the book? Here I
I'm
can.
looking at whoever's on a spreadsheet right now. I think it's Michael.
Yeah, I can go to it.
But
And
now we have a quick calculator, so you end up with 6 on that.
yeah, well, I'm sharing my screen too, aren't I? Or
All right, let me go to
no,
that
no, no.
one.
Sorry, you can go on, Michael.
No, it's fine. It just doesn't
So
matter.
I was just running the calculations.
He was doing the dimensions that would result. I think.
Yeah. So when I first started convolutions here, maybe
Yeah,
you
this
go
is
ahead
this
and
is
do
what I'm
that.
saying. No, but this is what I'm saying. What you're highlighting right now is what I was trying to say. I said it
Yeah.
horrendously.
Yeah. So
So, but
that's. I mean, I
I
think we
don't
were saying the
fully
same
get
thing.
how it ends up in an m plus whatever it was, m plus p minus one times
Yeah.
m
I
plus
don't
q
get
minus one.
we're exactly adding them together either.
Actually, look at your example. This is actually probably the right answer, honestly. So hold on, scroll up for a sec, if you don't mind. Okay, so we have an n equals 4, m equals 3. So you end up with a 6. So that's
You end
7
up with six,
minus
which is how
1.
many?
And then we should end up with it looks like a 4, I think. But so 6 is spot on with what you just said. Right? Because it's
Yes.
but I feel like I mixed some stuff up.
Well, I mean, I guess the reason it's confusing me is because the toplets, um, the dimension of the toplets isn't that, and then when you multiply it by one of the vectors, you end up getting the dimensions of what we were just showing.
Well, so wait.
Yeah.
Wait, but
That's the number of convolution.
when you multiply the tuplets, don't you get that dimension? Do you not? No, you don't. You don't.
Yeah, that's what I was trying to figure out in my head. I didn't think you did get that.
You don't. You
When you
don't. Well, of
multiply
course you
the
don't, right? You have a
Well, you
6.
got to remember, toplets is a separate function. So we're applying the convolution function. It's not a multiplication function. So in the most simplified form, you end up with 6.
Yeah,
When you
but
simplify everything from the convolutions that you're looking at right now.
the tuplets function you are doing multiple. Well, so you have a tuplets function, which I don't know what the tuplets function is. Let me start there. But the t of something creates a matrix, and then you are actually multiplying it. You're always doing a matrix vector product. You're doing two matrices, or
Yeah.
whatever it is. Right? So you have the convolution A star B. It's a linear function of B, and for fixed B, it's a linear function of A. It means you can express A star B as a matrix vector product because it's linear.
So let's go.
But,
Let's,
I mean,
let's go to the toplets function and change something. There's something that I wanted to change. Is that length? We can change
Wait.
it to.
Jupiter,
we're
Shane.
okay with the just to make sure we're on the same page. I will. We're just make sure we're on the same page. We're okay with the m plus n minus 1 though.
Gives you the number
Not
of
really. I
the number
honestly, I feel like that's lucky. I hate to say it, but I
the
don't.
number of
Yeah,
convolutions.
I feel like that might be lucky too.
Uh,
But what I was saying is, if you do this, which is take you could end up. This is more dynamic.
Shane,
So if you take
wait, one sec. Just because I don't think Shane. I think he's tentative right now. So, Shane, I think the reason that I feel like it's lucky because I feel like an n by m matrix is a single matrix, and then you have this other matrix. So, like, you have this PQ matrix and this NM matrix, and you end up with a situation that's M. You know what I mean? Like I don't.
It wasn't at the M plus
Right.
N
I
plus
think I
N.
said
That's
that, but I
P
think that
P
wasn't
minus
right.
one.
Is what I'm trying to say.
I missed that actually.
Yeah.
Well, here we go through N plus N minus one actually for the toplets.
Yeah. Well, let Michael say what he was
Okay.
trying to say,
Wait,
and then.
yeah. Sorry.
So we can change that length. So in the we can actually build into this function. Why are we feeding it B and we're not feeding it A? Is the question.
So that I think that touches on what John pointed out before, that the T of B and T of A are completely different matrices. At one point, you only take in one of them, and you're going to end up multiplying that by the other vector. So,
Okay, if you look at-
toplets will never need to take in A and B.
Okay,
It'll
look
only
at the
one or the other.
Julia. Look at the Julia book.
I'm sharing.
So
I'm sharing
you're
the.
taking length-
Yeah. Michael's got it. You can look at his.
Oh, you're sharing it.
I am, but it's okay. Go ahead.
Okay, so right here they're taking the length of A, but in theory you could redesign your toplets function. We could do it right now to
Yep.
accept B and A.
He's right. Okay.
And then we
So
can-
he's saying you could write it. I think you're saying. Correct me if I'm wrong. Michael's basically saying you could give the toplets function the two vectors, and he's saying that so n is really just the length of B anyway, or whatever. I don't know. Wait, actually, where do they use n?
Right. So if you
Oh, it's the length of A. Sorry. So to do the toplets function, all you need is the length of the other vector. So this toplets function that you wrote, Shane, has the B vector in it, and then it's got the length of the other vector.
And you give it the length of the other vector. Yeah.
Right.
Yep.
So you could feed it two vectors, and then
But I think they're correct that you don't need to, because you only need one or
Yeah,
the
I
other.
think you don't need to, but it would be
'Cause-
more dynamic if you did that.
But you're feeding it. Well,
It wouldn't though. I don't think it would be. Okay, let me think for a moment. So Michael's saying it would be more dynamic if you could feed the two vectors in instead of just feed. But the thing is, if you get down to the core of what matters is having a vector and then having the length of the other vector. It doesn't really matter that you even know the elements of the other vector. So the fact that if you want to send it two vectors, that will work. It's not going to fail. Like, you're correct, it'll work, but it just doesn't actually.
I feel like
we don't use the information
You're
of.
One,
you're sending information that's counterintuitive to what the actual toplets matrix is.
I mean, it's. I wouldn't say counterintuitive. I would say superfluous. It's
what
extra.
If you accidentally fed it A though, and you didn't know that you had to feed it B.
If you accidentally fed it A, you would have to also feed it the length of B.
Yeah.
Oh, okay.
Right? You can't. If you fed
I
it
don't know.
A and then give it the length of A.
User-
What?
Like, forget toplets. Let's call it convolve. And then if you feed it A and B or B and A, it's still going to give you the
Sure.
right answer. If,
So, yeah. So you could. I think this is kind of. So if I correct. So I'm gonna change these things real quick just to try and illustrate.
Do what he's saying. Yeah.
Tell me if I'm right. Yeah, that's what I'm gonna do. So if we created this convolve function, and then we gave it B, and then we'll just put A at the end here. Then you could do.
Well, what's n? I
and
don't
we-
even know what is
we-
n there.
we don't need N.
Yeah.
the length of it. It'd be like length of A, and I don't know if this is proper, but we'll pseudocode for a second. Length of A, and then length of A, and then okay, so all the n's are gone, and then instead of returning T, you would return T times A.
What? Wait. Everything I'm on board with except for that. Why do you have
Because
to
it's
do?
it's not a Tollpitz.
Oh, the convolution.
It's a convolution.
Oh.
So I think in your case where you return it to simplify it, I feel like this would be
So
more
run
proper
that.
than
Yeah,
to do
let's
it.
keep that, and then
Well, let's have two. Let's have two.
Yeah, yeah, yeah. I
You
agree.
have
I
to
agree.
you have to tweak it a little bit so it takes the greater of the two of them. If that
Wait,
makes
what?
sense. I think I'm not
No,
sure.
what do you
I
mean?
think
What do you mean? Say what you mean.
well, B is the longer of the two, which is why it's being fed in first. So you have to take the greater of.
Wait, wait, wait. I'm gonna challenge that premise for a second. Why does it matter which one's longer?
For the intermediary matrix, for the T matrix.
Hi, sweetie.
I,
I don't know why
I
it
mean,
matters which one's longer. I don't understand. What is Shane? What are you
base.
doing?
I'm writing the toplets right now.
No, no,
This is
no, no,
saying
no.
it's
It's
up
not
here.
that. It's not that. It's that you. Okay, it's not your fault. It's my fault. It must be my fault.
Um,
Okay.
yeah, I think Michael, I think I would challenge that too, just because the book, showed that you could do the toplets either way,
Oh, you
and
can.
then you and
Okay.
then you end up getting a different toplets matrix, just by feeding it a different vector. So instead of feeding it b and then length of a, you would feed it a and length of b, and you just end up with it.
Can
Based
we
on my
can we talk
understanding,
about the
right?
toplets though too, or not even just the toplets, but talk about both of these functions you just wrote? Because honestly, so there's some Julia syntax that I just want to clarify real quick. So you have you're saying t of a slice, right?
Yep.
So can we talk about what that slice looks like? So
Yes.
you're going 1 through m, so you're picking some integer, right? And then you're saying the length of the whatever. You're either saying n or the length of a or whatever it is plus m. What is the middle part of the? Is the middle part the steps that you're jumping? No, you don't have to
You
change it.
no,
You
this is
have the other function below you. You don't have to change it.
no, I'm not changing. I'm still leaving it. It's okay. I'm just setting n here, so it just makes it clear
Oh
how
yeah,
to
yeah,
do
right,
this.
right, 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 right.
So this is where we set it to all zeros, right? And then you remember in the toplets that there were vectors on the
Shane, you know
diagonal.
what? You know what you could actually do. You're
You
gonna
could do
laugh at.
width for
No,
T.
but you can even make your life a whole lot easier. You can call the toplets function inside of the convol function
Yeah, yeah,
Yeah,
yeah.
you could.
because you're
Yeah, that makes
returning
sense.
t, so you can just erase everything you wrote and just yeah, erase everything. No, literally erase everything. Yeah, 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 yeah. Everything,
Yeah.
everything.
No, I got it. Just give me a second. I got it. And even just give me a second. um,
You might have to put it below, but I think Jupyter will be fine with it. So t equals that, the result of the
yeah.
toplets.
So then this is the function you're talking about, right?
Yeah, yeah.
Okay. Um. Yep. So, but yep. So, okay. So toplets, John, you're right. So it's all zeros right now, but then we got to set the diagonals to the appropriate element. So this is
Hmm.
we're iterating through the diagonals. You go from 1 to m, but then 1 to m plus m, you end up getting diagonals, I guess.
Whoa, 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 man.
Um,
Whoa, hold on. Let's just talk about that for a sec. Sorry about that.
I is 1 to m, and then you
Actually,
go
they
from
they actually have it. I think I'm even sharing it. Yeah, I am. Okay, so the single indexes of the elements of the matrix BI and the matrix TB are I plus m plus n, comma, I plus 2 times n plus n, plus I times 3 plus n plus n. So it's skipping m plus n plus m each time.
it's skipping m plus m
Well,
each
it, it
time.
it's skipping that amount. Okay,
Yeah.
so if you have Jesus, we need to think this through. So
Okay, so let's just set like n equals 4. M equals 3.
No. Oh. Well, you don't have to do that. Just
Yeah.
make a b vector, and you can check it. I don't know what you're doing.
Oh yeah.
You have N, M, and P and Q.
He just needs two.
Well,
He just
wait.
needs b and n.
We want to wait. Do we want to run through act? Because that's what we're. I think that's probably.
I'm trying to
Right.
understand the function, honestly. So we get the length of the b, right? But we also need. You know
All right.
what's
So then we have.
okay? Okay.
You need the width.
This is probably not
Like,
not always the way to think about it, but b is some vector, right? And you're finding the length of b, and then you're walking through it, and then you're setting each. You're vectorizing this like this other zeroed function. This zeroed, so zeros is going to create some matrix, right? Like so is zeros takes in 2 dimensions, right? You're
this
right.
is zeros, right? Oh, zeros not defined. Oh, I
You
spelled
spelled zeros with it. You spelled it as if you were in Britain. Yeah, okay. So that creates some matrix, and then you're walking through the length of b, and you're setting each. For each. So you're saying 1. So for 1, let's set a slice of the matrix T equal to that. Oh, this is the diagonal. That's the that for loop is the diagonal. Yeah.
Yeah. Yeah.
Okay.
It's set in.
That
Like you're
is
setting. Yeah, it's a weird way to write. It's a very iterative way to write a diagonal, but yeah, that's what
that's
you end up doing.
awesome though. It's actually pretty amazing because so if it, so that means that like you're setting a diagonal. So b of I is the diagonal, by the way. So you're setting equal, so you're vectorizing the equal to b of I, right?
B of I is the element that's gonna go on the diagonal.
Yeah, exactly. B of I is the new diagonal, right? It's the element that's going to create an entire. Can you scroll up for a sec? So the part that's interesting and not painfully obvious is that the slice of t I colon n plus m colon to the end. So
Yeah.
the thing that's not obvious that is that in Julia when you have a matrix is if you do a syntax like that, it's going to walk. So in this case, it's 15 elements, right? So what is I? So I is 1, for example, the 0, 0 at the first element. And then it's n plus m to the end, right? So what is n, by the way? What
N
is
is
n?
the length of.
What is it? What's
Length
the
of
actual
diagonal.
number? 3 and 3?
3.
So it's going to start at 1, and it's going to set b of I. What's b, by the way?
B is 1, 2, 3.
Okay, so we're going to start at 1. So we're going to go 1, and then we're going to go n plus m, which is 6 more than that, which is not 6 more than that. It's going to go to 6. So actually, it is 6 more than that, right? We're going to go to the 7th one. So we go 1, 1, 2, 3, 4, 5, 6, 7. Is that right?
So here. So okay. So. Hold on. Let's actually insert one above. So I pointed it at. So I have it right here.
Oh,
So
m is 1. Sorry. M is not 3. M is
yeah.
1. So right, in this case, because you know why? Because you have an m, but you nested another m. Or no, you didn't.
No, the M is 3.
Yeah, so you're
It
stepping
is 3.
you're
And
stepping
is 3.
6.
So I iterates from 1 to 3, right? And
So you're starting at
then
1. Oh, wow, this is crazy. Okay, can you scroll up for a sec to the zeros?
start
This
at
is
1,
this
then
is
you go.
nuts, dude. The way this is actually working. All right, I'm sorry. I'm very impressed by this. So go up to the zeros for a second. Bless you. So the zeros starts at 1 and it sets it to 1, right? And then it sets a 1 7 later, 1 1, 2, 3, 4, 5,
Or later.
6,
Or
4.
later.
Why
Should
4?
be. Well, because the one gets set here, and then the one needs to get set here, right? Which is
Yeah, I know
one.
that, but how do you get a 4?
Yeah, I thought that was just like four away.
Yeah, how do you get the 4?
No, yeah, I haven't got there. I'm trying to backwards engineer that now because to figure that out, right?
Okay.
Um,
So n plus m is
is six.
6. So can you actually do you have a REPL real quick, or actually can you make another cell
Yeah.
and then make a vector of some length. Actually, it doesn't even like do t or something, and just do t. Yeah, yeah. Do t in front of that, and then do you know 1, and then set n plus m to the end. Yeah, same thing. Same thing you see there. Yeah, yeah.
Same thing I
Exactly.
have down here.
Exactly. Exactly. We don't even need to save it to a variable, but oh shit, because you set it.
I set it already. But
They would otherwise all be zeros.
yeah, I have
Yeah.
it the same thing here too, all ones. But
How?
so
So
how is the n plus
all right, all
m
right, all
to
right, all right, all right. Can you do a different thing? Can you do a different thing? Can you do like a range in Python? So can you do like you might have to can can I just share my screen real quick? Because I know that
oh my
it's
I got it. I got it.
what?
So you're skip. So you see here, I didn't realize. I thought we were skipping on the rows, which is where I was confused. But now the seven makes sense because that's the length of the row. So you see right here, I just did t one two.
Okay.
So skip by
Okay.
two to the end. So then you get 1 3 0. So which is you get 1 3 0. Skip by 2 1 2 1
How?
and then 3. So now the 7 makes sense, right? Because, where's my t?
So how are you
Uh,
go skipping by row by
so
column
you
though?
so you said 7, so you start with
I mean, I
1,
get
then
it.
you
I
go
get it. I get it. I just
or 6, I mean.
no. I get what you're saying. Like it's 6 because it's the length of the rows, right? It's a
Yeah,
5 by 3, so you're skipping.
yeah.
So you're starting at the first one, skipping 6 of them, and
But
going to
how
the
are you?
seventh ones.
Why does it skip by row? That doesn't seem like
Yeah, exactly. That's what I'm saying.
that's
That's
literally what's happening, though.
crazy.
That's literally what's happening. That's interesting. That's weird. Um,
It's probably not
okay.
weird. It's probably just us. But okay.
It's a sequence, and then
Yeah, it's just
I
my
just thought
issue was I was counting the wrong way. I was counting the way Shane's highlighting right now,
of
where I
course, yeah.
it's not down each row. Like he's going.
you have to go down.
Oh no, Shane, it makes sense. Hold on, let me think about it for a second. It makes sense because if you have so an array is a list of lists, right?
Oh, if you do T1, you're gonna get, or
The
no,
part that I'm a little unsure of. Wait, can you?
that's not gonna work. Um, all right. Well, I mean, I'm okay with that. That's literally what Julia does when you skip by elements.
No, I'm not okay with that at all. Like dealing with that way. So T is a matrix, right? Hey, Colby.
Yep.
So you end up taking a slice of that matrix.
You know, you take you get a particular, uh, you get a particular element. Or no, yeah, it is.
That's
It's
the
a
part
slice.
that
Yeah,
blows my mind.
yeah. So you end up getting a slice, but you vectorize it all to be the same element, right? You
Well,
set each element.
that part makes sense. It's the T part, the I to the n plus n, what you just showed with the 2 thing.
So your
That
slice ends up being the diagonal, though. It
no,
is a slice.
I get that, but wait, if you scroll up to line in input 61, that 66, that doesn't, that I'm confused about. That right there.
Okay, so
66.
yep. So you understand how it got this by jumping
Yes.
by twos?
I do. But I don't understand why it actually did that. Because I thought that it was a list of lists. So, for example, if you did T, so can you line 69, can you just do T colon, so do
Well, if
T,
you change it to 4, you should end up with all ones then, right?
well, 6 7 will give you all ones.
You changed if you skip by 6,
Yes.
you would end up
Yes,
with
that'll
all
go
ones.
all ones or all twos or, well, no, 6, keep it at 6, but change the first element to 2 to 3.
Yeah,
You know,
then you get twos, and
then you'll get
yeah,
twos. Yeah,
but
exactly.
you you don't like why
It's not that I don't like it. I just don't understand it. So if you go to the first thing for a second
yeah.
and you do a hard bracket colon comma colon. Well,
Uh
colon comma colon. Yeah,
oh, colon comma like that.
yeah. All right. So then do a 2 in front of the first colon.
2 comma
Yeah, that
or
just leave
yeah.
it. That's good. Do that. Oh, end. Do end at the end of that one. Not at the
Oh,
end. No.
oh,
Yeah, right
that.
there. Yeah. Okay, so now can you do 2 colon
Let's
2
have that. Just
end? So just add another 2 and then end. Yeah. Okay, so what's the original matrix? It's the one on top of it. Right. So it skipped every other row.
skipped every other row. Yeah, so you get the 2
Yeah.
1 0, and then you get the 0 3.
So the number in the middle is the skipping.
But it kept the rows. See, this is the part. So if you take out, okay, so take out that last colon, and it's just going to have a 2 and a 0, or a 2, a 0 and a 2. You know, like
2
that part.
0.
Wow. Okay, so what Julia's doing, what's super interesting about this is what Julia's doing is it's running through all of them. So it's treating the 5 by 3 array as
Really, it's like a 15.
a 15. Yeah. That's exactly
So
what's
they,
happening.
they mentioned that it's like a flattened
It's a flattened
array.
array. Yeah.
Thing.
Wow. Okay. That's exactly what's going on. See
Yeah,
that?
but in theory that should be a 6 there because you want to get all the ones. so
Yeah,
it should be a
yeah.
zero.
It is a 6, right? Yeah.
Yeah.
Oh, you get a 6 right here. You get your column. Like
Because it's every sixth number is a 1.
Right, but if
yeah,
you don't know that
And-
that's a flattened array, then
Yeah.
that doesn't make any sense.
So yeah, it seems simple, but yeah, I'm totally with you.
And we know the way
Yeah,
to
it's a
dynamically
array.
calculate.
You have to know you're getting a slice. Then you have to know you're vectorizing it from a constant.
Right. It's got Julia syntax in it that is not, you wouldn't know by reading that. Is all I meant. That's fine. I'm actually fine with it now. I didn't realize, I should have realized that. It should have.
I think our convolve function is messed up.
Yeah. So why? What is messed up about it?
Well, for one, we're not using, and we use n below it. Okay.
All right, keep writing. I got to use the bathroom. Be right back.
I think. Well, we'll see. It might be because we just made this, right? So it might be messed up.
Yeah.
But we'll see. Let's see. Um. And you have TV. Length of
Well,
A.
Try convolve.
Yeah, we'll do both. So that's our matrix. And then their next line they actually do. Their next line they do TB times A. Oh, then they get this, and then let's try convolve. What was it? What did convolve take? B and an A.
That's the reason why I said it should be two matrices. Yeah. Okay.
And we get the same thing. Or convolve.
So we know that the default convolution function is wrong in DSP. I mean,
Well,
to me, that's basically like.
Yeah, that's what I was trying to say
Sorry, I'm
before.
back.
Well, actually, convolve is giving us the same answer now.
Wait, are we correct
maybe
now?
it was in your memory.
Wait, hold on. Do we have the
So-
answer that we were looking for in the beginning?
Well, I think we proved that the convolve function is correct.
It's correct.
Maybe
You had a memory error, and I've had that before. Remember? I had that early on.
Are
I was
you
getting all the wrong
serious?
numbers.
I think the book might be wrong. Honestly, guys, I think the book might be wrong. I think if I go run this, you get 4. Yeah. Uh, the com function seems to work. Let's run ABC. You have A, you have B, you have C, and we want to run conv of ABC. Oh,
It was the memory error. That's an error to show Julia.
yeah.
I had that in one of our early on thing. Remember, I was getting all the.
We should have
numbers,
ran the
figured it out.
vectors and take a look at them because that's
yeah,
hilarious.
that was a bad debugging. I feel like or maybe yeah.
That's a really scary error, though.
So, John, our convol function that we made, which did the exact same thing that we're doing, obviously worked. TB times A afterwards, we get the same thing, and then conv, we get
All
the same.
give the same answer. Yeah.
All get the
All
same
right.
answer.
There's some sort of glitch in Julia that we should tell them about.
Are you sure
No,
it's
that
not a
happened to me.
glitch in chain? Or
Well, it's like a memory error.
Yeah, I mean, I think I probably ran A, B, and C, but who knows if my.
I know you ran them. I saw you run them like
Okay.
multiple times. I've had that
Yeah,
error
video
before.
proof, thanks to our streams.
it's true.
So
Yeah,
now
it's
we're
funny
doing it.
because I started get the DSP package, but I didn't actually do it. Like I started doing it, and had I done it at the time, I would have been able to be like, oh well, no, I got what they got. You know what I mean?
Do you understand why I say that's a really scary error? It's like
I understand why you say that, but I'm not convinced that. No offense, Shane. I'm not convinced that it's not something he did. But let's just see. Let's just see. What I just ran it myself, and let's just see what happens.
I think it's a memory glitch.
All right, look. I just ran it, and I got the two. So the thing is, we don't know how he got those other numbers.
We have video proof. So
We don't exactly though, because we don't. The problem is we don't know what A and B were defined as. I mean, yes, I guess we do have video proof that, yeah, maybe we redefine them or
I might have
something.
messed up. No
I mean, I'm
idea.
hoping
might
you
have
did,
messed up.
just because I got the same thing that.
VMLS.norm, right? Yeah.
But if you're doing like financial risk or something like that, and you get that memory error, it's like a huge or accounting.
Yeah, but I don't know what happened. I don't know that it was Julia.
I can tell you that that's happened to me before too, and I run everything and I did. It
There was
properly,
okay.
and I
Let's
restarted.
be 100% clear. No error showed up on the screen.
Yeah. There's no.
on yours, yeah.
Right. So that's why I'm not convinced that it was an error versus
I think it was stuff that was stored in memory.
yes.
Junk, and I think it was like picking up that junk and plugging it into the.
Yes, that makes sense.
Yeah. Yeah.
That's basically what I'm saying.
But I feel like there's two options here. Either I messed up, or stuff was stored in memory and it retrieved it kind of wrong, I guess, is what you're saying. It's probably more likely I messed up, but Yeah, I don't know. I guess maybe it's a Julia thing, a Julia and Jupiter thing. I'm not
I
sure.
mean, like, imagine if you wrote a huge program in Julia and you were having this error and you couldn't figure out what was causing it, and people call you over to their desk because I've had this with programming languages before. People call you over to your desk, but you just can't replicate it, and then it just pops up every once in a while.
Yeah.
That's like a tormenting error. It's like
Yeah,
a
I'm just
terrible
not
error because your
convinced that's
program.
what happened yet. I hear you. Um,
Uh,
but
so I ran the at time macro with just the multiplication, our function that we created, and then their function for convolution, which got the same results. And it looks like it's like they did it when they did it, they got it a lot faster too.
hmm
In our case, it was like 9 times faster. Their function, so they're doing more efficient than what we did, which
Yeah.
isn't too much of a surprise.
so in the time function, do you actually have to save it to a variable, or they're just because they're gonna use it? Nah, it's just because they run a normal variable on it. That's why.
Yeah.
It's just they saved it, but they
Uh, and then wait, so what's the last thing they're doing here? Finding the norm between toe
so
uh splits.
is norm a normal random variable with that mean? Is that what it is?
Uh,
What is that? My guess is it's a normal random variable with that mean.
norm v, you just get
Oh,
7.0.
it's a vector. Why is it a vector? Oh, convolution is a vector. Sorry. So okay, so you're giving it a sort of a data set. You're giving it an array. Sorry. So what is norm doing? So if you give norm a vector, what is it actually doing? Yeah, what is it doing,
It's
Shane?
calculating a typical number. That's what
Yeah,
it's
that's what I
doing.
think too. I think it's giving you a norm. Compute the p norm defaulting at p equals 2 if a were a vector. The p norm.
This was like early on in the book. We went through
Yeah,
this.
they did go over it earlier. Um,
Let me
So
find
it's
it.
giving you a normal variable in that vector space.
but that but the thing is, like when I did 1, 2, 3, you get 3.7.
Uh huh. Yeah,
Um,
because it's a random one. Like, what if you did? Um. So wait. So
It's the Euclidean norm of an n vector is denoted with the double absolute value.
oh,
It's
oh,
the
yeah.
square root of x
oh, it's
transpose x.
that. It's that.
Yeah, it's that. Yeah.
Oh,
It's the double bar. It's the double bar absolute value
got it.
in the text. Yeah,
Well, it's the
no, that
absolute
was
value over. Isn't it
no,
over
No, it's
n?
x trans.
I said the double bar absolute value is how they denoted in the text.
It's
So
Like
over
compare
n,
both
right?
values. Yeah.
yes, yes. Um, that's just yeah. I mean, we've used it a lot.
I was thinking of a
um,
a random normal, but
this is what
it's
I meant. This is what I meant by the double bar, right? And this is how the text denotes it too. It's a double. I called it the double bar absolute value. Um, the square root of all the elements summed together squared. Um, so in this case, with the 1, 2, 3,
wait. Say that again. Slow
uh,
down. The square root of
this
all the elements summed together squared. So the sum of all the
so
elements squared.
1 plus 2 plus 3.
1 squared is 1, 2 squared is
Or
Can you
4,
just do it
three
out?
and
squared
Just
is
cause
9.
it's easy enough.
Yeah. So
So
then
before you write it all out,
you
can you
how do you
actually just
square?
do? Can you actually just do the vector? No, no, don't do that. Hold on. Let's do it the Julia way, right? So do the 1, 2, 3 dot. Okay. A, yeah. Dot, what? No, not dot
What is
equals.
it?
Dot square. So put in paren. Okay, erase that.
Uh,
Erase that. Put in
yeah.
paren. Dot paren.
Dot paren
Square 2.
square two.
Right, but I don't know where the B is coming from. So just do A or whatever. Something like that. Yeah, nah. So,
A equals
I
A
mean,
dot.
how do you do that? All right. Do like instead of dot square 2. So can you change the A to a 2
Okay.
space and then
Okay.
put an A at the end. Space A. Yeah, something like that.
That.
But take out the 2. That 2. The middle 2. The middle 2. The middle 2. Yeah.
That.
Oh, I think it's the other way around. My bad.
Yeah, be
Yeah.
a squared.
Yeah. Something like that. Did did it
Uh,
run? I can't see.
no, yeah, it ran.
What happened?
Just doesn't. It doesn't like. It says space before. Oh, let's not put a space.
Mm,
Extra token two at the end of expression.
hold on. All right. I mean, do it whatever way you want.
Uh, I felt like you could do. Couldn't you do like the dot equal b dot equals a squared or something?
Yeah,
Yeah.
but oh, you know
Put
what?
a dot in front of.
I
Put
just
a
looked. I
dot
just
in
looked
front
it
of
up.
the.
I just looked it up. Just do A dot square 2. That's all. Just put
Yeah,
it.
that's what I was gonna say.
Yeah.
Oh,
Just get rid of the
a
B. I don't.
dot
Yeah.
squared.
Yeah,
Yeah,
just
like
like
that.
that. Yeah.
There you go.
There you go.
And then
And now you raise
you
it
find
to
this.
half power.
Well, you gotta. How do you find the sum?
All
Maybe
right. All
find the
right.
sum.
So hold on. I don't know if sum is the or sum one of them. Yeah, sum. It's just sum.
Probably just some.
Yeah.
Sum, and then square root.
But just use piping because this is getting a little out of control.
You love piping, right? I'm
Because
always like,
you know why? You know why? Because a human being doesn't go, well, it's the sum of the square of the whatever. They go, oh, square it, then do this, then do this, then do this. Like that's why I like piping because this, what he's writing right now, is not how human beings think of it. How human beings think of it is square it, sum it, then find the square root.
yeah, I get that thinking. I just don't think that.
No,
I
there's
think for
wait,
some
wait, wait a
reason,
minute. Are you telling
maybe
me? Wait a minute. Are you telling me that if I tell you to find the norm of this, that you think of the square root first, then you think of
no.
the
I
sum,
just
then you think
when
of
I
squaring each element?
Yeah, I mean, it's all good,
what
right?
I do
This
is I write. I
is an
the same way
approach
you
that
did it. I do it from the inside out. So when I build it, I build it from the inside
So
out,
you
and
do
that's
it the
what
way
makes
Shane's
fun.
writing it now. That's the
In my
inside out
head, though,
approach.
I do that like automatically. Like
Yeah, I
Right.
don't use this either.
You
But
don't,
it's
you don't,
very-
but no, you literally do. Here's what you guys do. You take line 122 and you translate it into 121. That's what you guys are doing.
yes,
And I'm
exactly.
saying, why even translate it when you don't need to?
So now we
Probably more efficient.
now we see how the norm is calculated. And we thought we got confused for a second with what we
Yeah. That's the norm. Yeah.
Um, so yeah, I mean so the last thing we need to figure out is why are they finding the norm between the difference between these two things?
That's a good.
Uh,
That's right. That's the
uh,
question. Yeah.
uh, TOEIP minus the convolution. TOEIP
Oh,
minus the
oh,
convolution.
they're just okay. So they're trying to say like, what's the difference between these two methods? I guess.
Uh,
It
oh,
should be like 0, basically.
oh, because
It,
this is
it should
time,
be
right?
0.
This is
Yeah. So time. So see, what is C?
I think
Yeah.
the time macro is something though. What the hell? Oh, yeah. What
Well,
the hell?
that's you're going to get a
Oh,
vector
that's the
back.
convolution right there.
In the convolution, you're getting a vector back.
Yes, so you get a convolution. So why are you subtracting the towit from the convolution, or the convolution from the towit?
What's the toe up is also a vector, right? So
Yeah.
It's using the other function. It's
it's
one.
c
It's the
toe
slow
up or
way versus
whatever.
the fast way.
Well, yes, but it's not just that. There's a different. The point is, what I think Shane's asking.
Oh, I see what you're saying. So they're just trying to find the difference between our function. Oh, so c toe up was literally our. So see, this is what confused me. C toe up is literally the convolution. It's the toe up function times a. So I was confused there because I thought it was just the toe up matrix, but it's not. We're multiplying it by a, so you end up getting the convolution.
Right,
So what
but
they're
but
doing,
but but why the norm?
so then they're trying to find the difference between all of our convolutions and all of theirs.
Why
So
is
I
there
guess
any
what they're
difference at all?
yeah, I guess they're trying to say that there's some error at each at, with our either ours or theirs or something. Right? They're not the same, and that's their point. But the error is really small. 10 to the negative 12.
Yeah.
That's
So there's once
interesting
again
that there's an error. Like,
there's a difference, or there's rounding that happens in whatever it is. Maybe in order to make theirs so much faster, they need to make certain assumptions. But I guess the
no, I
point
think the
is that they're
Toplets one is making the assumption because that's
no,
the no.
because the Topless is the one we made, which was literally just multiplying by the matrix, right?
Yes.
To
Unless
be
we did something
precise.
special.
Because we did multiply by the matrix. Yeah.
So I think so. I don't know, but theirs. This one is way faster. It's 9 times faster in the case we ran, and they're about the same. But
Yeah.
there is a difference. That's kind of what I'm taking away.
All right, but you're assuming that the difference is on this side of they made assumptions in the
No,
convolution
no,
to
no. I
make it
won't make that.
faster.
That's a possibility, right? I have no idea
It could
about
be
the
they're
difference.
using a
That's
different float. It could be they are
it's a possibility.
calculating it a different way and it's faster, but
Maybe assumptions, maybe rounding,
it could be
maybe
Taylor series of some kind.
yeah, but
I
they're
don't know.
close enough. I guess,
Hmm.
right?
Okay. All right.
It's interesting.
It's interesting enough. Yeah.
Right?